This video will briefly introduce a compact beam steering metasurface lens array antenna with low-cost phased array. The relevant work can be found in XII transactions on antenna and propagation. Beam steering and multi-beam techniques largely facilitate the design of beam directional high-gain antennas. Phased arrays achieve agile beam scanning using active components such as phase shifters. However, the heavy implementation of phase shifters would incur high power consumption, high cost, and immense hardware complexity to the system. Recently, metasurface lens antenna is developed to achieve beamforming without any phase shifters. However, the focal length, which has a typical value of 0.5, can hardly be reduced for sufficient aperture efficiency and gain. In this paper, a metasurface lens array architecture is proposed to provide a trade-off. By dividing a single large aperture lens into n small aperture lens elements, the overall thickness of the proposed antenna can be reduced by n times. Moreover, less phase shifters are required compared to phase arrays with the same aperture size. The beam steering is achieved in two steps. First, the main beam directions of the lens elements are switched over a large angular step by selecting different feed excitation beneath each lens element. Then, the switched beams are fine-steered through phase shifters. By dedicatedly locating and feeding the antennas with required phase shifts, a wide and continuous beam coverage range is obtained. A metasurface lens array antenna with 3 lens elements is fabricated to validate the idea. The feeding structure for experiment is simplified. Instead of employing a switching network, a single feeding antenna is located beneath each lens element with necessary offset to achieve beam switching. The required phase shifts among elements are realized through the varying transmission line lengths. The proposed antenna achieves a 3 dB beam width coverage range of ± 30 degrees with a maximum gain of 19.1 dBi and a gain tolerance of 1.6 dB. To conclude, the proposed architecture is a hybrid approach of conventional phased array antennas and metasurface lens antennas. Comparing with conventional metasurface lens antenna, the proposed antenna is compact with the focal length reduced to 1/3. Only 3 phase shifters are required across an aperture size of 7.2 lambda. More details of this work can be found in the reference. Thank you for your attention.
This video will briefly introduce active cylindrical metasurface with spatial reconfigurability for tunable backward scattering reduction. The relevant work can be found in XII transactions on antennas and propagation. Most of the traditional metadevices for backward RCS reduction cannot be dynamically tuned once fabricated or just with limited working bandwidth. Revoking the passive constraint by active metasurface loaded with tunable components will open up a way to manipulate the performance dynamically, thus providing possibilities to realize time division multiplexing of operating spectra to equivalently expand the bandwidth. However, it is still challenging to design ultra-thin conformal metasurface capable of well-suppressing backward scattering with widely tunable operating frequencies. To overcome this problem, this work presents an active cylindrical metasurface with spatial reconfigurability to achieve dynamic control of the RCS reduction. We start from designing a passive conformal metasurface to suppress backward scattering by using the composite strategy to improve the operating bandwidth. To equivalently improve the operating bandwidth via time division multiplexing, we finally implement an active cylindrical metasurface by loading voltage-controlled PIN diodes on the modified passive metasurface to achieve tunable RCS reduction bandwidth assisted by spatial reconfigurability of metasurface structure. It is noted that conventional metasurface with PIN diodes only have limited abilities in tuning the working frequencies, for example, switching between 2 frequency bands. By introducing the concept of spatial reconfigurability, this work proposes a method to realize versatile surface impedances of a metasurface by switching PIN diodes only, and addresses the issue of achieving flexible tuning of working frequency over continuous and wide bandwidth. We then fabricate an active metasurface prototype. Both simulated and measured results demonstrate that by reconfiguring the metasurface spatially, surface impedances can be manipulated dynamically, resulting in high-efficient backward scattering within a broad continuous and dynamic band while keeping its ultra-thin thickness at lower microwave frequency. More details of the work can be found in the reference. Thank you for your attention.
Hi, my name is Kelvin Nicholson and we're here at the Defence Science and Technology Group in Australia. As part of the aerospace division within the Defence Science and Technology Group, we have an interest in multifunctional composite structures, and more specifically ways to integrate antennas into load-bearing glass fibre laminates that you might find on uninhabited aerial vehicles. The types of antennas we're interested in for these multifunctional composite structures are of the two-dimensional metasurface antenna variety. They're useful in our application because they can be implemented as a single ply within a composite laminate. How we design these antennas is quite neat. We borrow a trick from holography where we take the interference pattern formed by two waves. These waves are of course the objective wave, the radiation pattern we want to emulate, and the reference wave, which is the way we excite our surface wave on our geometry. When you have this interference pattern, you can then map it to an impedance, and because we have a TM mode wave, that impedance is inductive and is governed by the amount of copper in each unit cell. Now classically these unit cells are rectangular in nature, but the trouble with a rectangular unit cell is it doesn't drape or conform nicely over an arbitrary geometry like a conformal surface you might find on a UAV. So what we did is we went one step further and borrowed some of the work from Dan Siebenpiper, where we implemented the Voronoi partitioning of a surface, which means we can create nice conformal non-uniform unit cells over an arbitrary geometry. The trouble with this approach though is you can't neatly describe your reference wave, the cylindrical wave that you would have on a nice planar surface, in a theoretical way very easily. So we used a numerically simulated reference wave from CST. And the same for the objective wave. We used a numerically simulated objective wave from CST. And the result was quite a neat conformal metasurface antenna with a nice pencil beam radiation pattern.